Hi, this is Sai Potana, founder at embeddedystems.ai LLC. In this video, I'm going to go over quantization in LLMs, that is large language models. Section 1 describes quantization across the life cycle of a large language model. Quantization spans the entire lifespan of a large language model from training to deployment. Quantization can be applied during training, after training, during inference, and even inside runtime memory like the KV cache. Each stage offers a different trade-off between accuracy and efficiency. Apart from simple quantization techniques, there are some advanced techniques like GPTQ, AWQ, QuadJ, and TurboQuant. These methods target different parts of the system like weights, activations, and even runtime memory like the KV cache. Section 2 describes training time quantization, commonly known as CAT. In quantization-aware training, low precision is simulated during training using fake quantization nodes. Fake quantization nodes are inserted into the compute graph so the model learns to operate under reduced precision like int8 or fp8. Gradients are still computed in higher precision, but the forward pass reflects quantized behavior. The model learns to adapt to the reduced precision like int8 or fp8 while still training in higher precision for stability. This produces the best accuracy but requires retraining and significant compute. Section 3 describes post-training quantization, also known as PTQ. In post-training quantization, a fully trained model is compressed after training. A calibration dataset is used to collect activation statistics like ranges or distributions. Weights and sometimes activations are quantized into lower precision formats like int8 or int4. This approach is fast and widely used in production, but may introduce some accuracy loss. This is where most modern methods come in. After training, a model is quantized using calibration data. Now, instead of simple int8, there are some advanced methods like GPTQ, which optimizes weights using second-order information, AWQ, which focuses on preserving important activation patterns, QuadJ, which jointly optimizes quantization across layers and data distribution. These methods significantly improve accuracy at low bit width like int4. Section 4 describes inference pipeline with quantization. During inference, quantization plays a major role in performance. Weights are stored in low precision format like int4 or fp8. Compute is performed using optimized kernels that understand these formats. The KV cache, which grows with sequence length, can also be quantized to reduce memory footprint. However, sensitive components like layer norm and logits often remain in higher precision to maintain stability. This mixed precision approach delivers both performance and accuracy. Section 5 lists popular PTQ methods. GPTQ focuses on weight-only quantization with minimal reconstruction error. AWQ improves int4 performance by preserving highly important weights. QuadJ goes further by jointly optimizing quantization across the network. TurboQuant shifts focus to runtime memory, compressing KV cache instead of weights. Each method represents a step towards more system-aware optimization. Section 6 talks about where quantization happens in a transformer. Inside a transformer layer, quantization is applied selectively. Linear layers and MLPs, the most compute-heavy parts, are quantized. Attention uses KV cache, which can now be aggressively compressed using TurboQuant. However, normalization, and residual connections remain in higher precision to preserve model stability. This selective approach balances efficiency and model accuracy. Section 7 talks about what gets quantized. Multiple components can be quantized, like weights, the biggest memory savings. Activation reduces bandwidth and compute. KV cache, now a major target with TurboQuant. Gradients, mainly during training. Different methods target different components and combining them gives the best results. Section 8 describes trade-off between precision and efficiency. As we move from FP32 to FP16 to FP8 to int8 and to even int4, memory usage decreases, throughput increases, but accuracy may degrade. The goal is to find the optimal balance depending on the application. TurboQuant pushes even further, effectively reaching around 3-bit equivalent compression for KV cache. Section 9 lists common quantization formats. BF16, FP16 widely used in training. FP8 emerging standard for high performance inference. int8 is the production baseline. int4 is aggressive compression. NF4 neutral network optimized format. The choice depends on hardware support and accuracy requirements. Section 10 describes quantization benefits in inference. Quantization enables lower memory usage, faster matrix operations, larger batch sizes, longer context windows, lower cost and power. These benefits are essential for deploying large models at scale. Section 11 talks about quantization granularity. Granularity affects accuracy and efficiency. It's usually per tensor or per channel or per group or per token. Section 12 describes TurboQuant, a new KV cache quantization method from Google. This is one of the most important recent developments. TurboQuant focuses on compressing the KV cache and not the model weights. It uses PolaQuant to transform vectors into a comprehensible representation. QJL to correct quantization errors. This enables extreme compression down to around 3 bits with minimal accuracy loss. The result is much smaller memory footprint, faster attention computation, and significantly longer context support. To sum it up, quantization has evolved from simple weight compression to a full system-level optimization. Earlier methods focused on weights. Modern approaches like AWQ, GPTQ, and QuadJ improve accuracy at lower precision. And now, TurboQuant extends quantization into runtime memory, fundamentally changing how LLMs scale. This is what makes large-scale, efficient AI systems possible. Thank you.